Hello, ladies and gentlemen. This is Miss Stover. Today we're going to be talking a little bit more about covalent bonding and how elements actually are attempting to share electrons. So first, let's talk a little bit about what a covalent bond does. So we're going to look at some bonding models for a substance called methane, CH4. Models are not reality. Each model has its own strengths and limitations. So let's look at four of them. So here we go. The first one is this kind of space-filling model that shows us a three-dimensional kind of idea. That space-filling model involves lines and other things that are going to help us better understand. So if we look at these things right here, we can see pretty clearly that we have some different ways to represent bonds. And each of these represents a pair of electrons. Now the way they're represented has to do with its orientation in three-dimensional space. So this is trying to show that this bond is back, this bond is also back, and this bond is coming out forward while this bond is going straight up. So that has its strengths. Then we see these three. This is one that just shows you everything. There's the carbon that's supposed to be in the center. It's not listed, but it's there. And then the four hydrogens on the outside. This is called the stick model, where we see the carbon and where its electrons are and the hydrogens, each of them here and here. And then this is called the space-filling model. The space-filling model is exactly what it is. This is how much space this atom would take up. Now, obviously, it's been blown up quite a bit. So, but it gives us a representative idea of how much space it would take up if we could see it that small. So they're all just really models that we can see. So we represent things in different ways, but we're going to today focus a little bit on Lewis structure and octet rules. So the first thing we need to talk about a little bit is the octet rule in covalent compounds. So first, covalent compounds tend to form so that each atom, by sharing electrons, has an octet of electrons in its highest occupied energy level, which is the same as we've talked about before. Octets are important. Covalent compounds involve atoms of only nonmetals, so they will share because only nonmetals will share. The term molecule is used exclusively for covalent bonding. So just some words here that we're talking about. So we know that they're sharing electrons, we know that covalent compounds are only nonmetals, and we know the term molecule belongs to covalent bonds. So the NOC rule. This basically describes what's going to happen to hydrogen, oxygen, nitrogen, and carbon when it's doing bonding. So hydrogen and all of the halogens will form one covalent bond. Hydrogen and any halogen will form one covalent bond. Why? Well, hydrogen has one valence electron and wants two. It has one place to bond. All the halogens have 7 valence electrons and want one more to complete their octet. So while hydrogen wants to be a duet, the halogens want to be an octet, but both of them complete that by sharing one electron with another substance. Oxygen and sulfur need 2 covalent bonds to form an octet. They have 6 valence electrons, so that makes sense. I need 2 more electrons to make that. So they want to form 2 covalent bonds. Nitrogen and phosphorus will form 3 covalent bonds because they need 3 spots. They are 3 electrons short of an octet. They need 3 spots filled with electrons. And finally, carbon and silicon, they very rarely ever form an ion, so they want to form 4 covalent bonds. They want to somehow get 4 electrons to be shared with them. Now, there's something very interesting that we need to look at. Hydrogen and the halogens will only form a single bond. They will never form a double bond unless the halogens in specialized locations. But single bonds are always formed by hydrogen. Oxygen can form a double bond or 2 single bonds. One double bond gives it 2 electrons, 2 single bonds gives it 2 electrons. So either way it can happen. Nitrogen can go a couple ways. It can form 1 triple bond and get 3 electrons. It can have 3 single bonds and get 3 electrons, or 1 double and 1 single and get 3 electrons. You get the idea here. The number of bonds, the triple, double, and single, talks about the number of electrons being shared. So a triple bond is going to share 3 electrons. A single bond is going to share 1, and a double bond is going to share 2. So carbon we'll get its by either 2 double bonds, 4 single bonds, a triple bond and a single bond, a double bond and 2 single bonds. So there's all kinds of combinations that we can have, which is one of the reasons why we talked about today. We can form more than one compound from the same pair of electrons, or same pair of elements, because I can rearrange my my electrons in order to give me the configuration that I want. So Lewis structures, what does it mean to be a Lewis structure, and what does it mean to do what it needs to do? So Lewis structures are basically ways that we represent elements. So Lewis structures show valence electrons. We've seen Lewis dot structures. We've done it. All you're doing is putting dots around it that show valence. Now we're not worried about charge right now because these are not ions. These are sharing electrons. So we worry about the Lewis structures. Lewis structures reflect the central idea that stability of a compound relates to the noble gas electron configuration. So we go back to the noble gas, we go back to trying to get an octet. Shared electron pairs are covalent bonds and can be represented by either dots, 2 dots being a covalent bond, or a single line being a covalent bond. So here we go. Completing a Lewis structure for H2O, dihydrogen monoxide, or water. So make oxygen the central atom. The reason we make oxygen the central atom is because oxygen 1 is the bigger of the two. It has the higher. Hydrogen is usually not used as a central atom ever. So it kind of breaks the rules a little bit because you're supposed to use the lower group number to make the central atom. But oxygen has more bonds to make. So oxygen becomes the central atom. So here we go. There's oxygen as our central atom. And we also have 2 hydrogens out here. So we have a total of 6 valence electrons here with oxygen. 1, 2, 3, 4, 5, 6. And 1, 2 for each of the hydrogens. So that's a total of 8. So add up the valence electrons. So there are 6 for hydrogen, 2 for hydrogen, 6 for oxygen, for a total of 8. So that means that oxygen will come in with these 2 hydrogens and will do something. Now that we know that there will be enough electrons to complete the octet for oxygen, we're going to be okay. So, but why is it that hydrogen does not need an octet? Why is hydrogen going to be satisfied with sharing just 1 electron with oxygen and 1 electron from itself? Well, remember, hydrogen is that special case where it just needs a duet, not an octet, to be like helium. So here we go. Join the peripheral atoms to the central atom. So there's our central atom. There's a peripheral atom, there's a peripheral atom. Well, look at there. We now have the dot structure for water. You can see that we have hydrogen coming in and sharing electrons. So this is 1 bond right here. Here is your second bond. We could represent that also like this. We could have O with H and H. We could do it like that. Okay, and there are other ways, but that's another way that we look at that. We'd also want to put the dots to make sure that we were showing all the valence electrons are full. So now we can see that oxygen has 8 valence electrons, and we can see that each hydrogen has 2. So we now know that all the necessary octets are complete because of that. So we see that. So here's the next one. Here we go. We have completing the Lewis structure of chloromethane. Basically, this is called chloromethane. Now, you won't need to know that name because we are not naming anything past binaries. So we want to first add up the valence electrons. So if we look at this, we're going to make carbon our central atom. We're going to make carbon our central atom. Carbon is in the lowest group from chlorine. We don't count hydrogen in the lowest group, so carbon is in the lowest group. It's group 4. This is group 7, so carbon is going to be the central. We can see that we have 4 from carbon, 3 from hydrogen, and 7 from chlorine. That's a total of 14. Now remember, you would think that we would need 16, but remember, this guy needs 8, but he only needs 1. This guy needs 4, and these guys need 1 apiece. So we're going to work that out. So next, we're going to start making carbon the central. Oh, this is out of order. Okay. So the question is, will there be enough electrons to complete the octets needed? Well, let's see. So join the peripheral atoms to the central. Here we go. There's hydrogen, hydrogen 2, hydrogen 3, and there is the chlorine. Now let's double check. So we have 2 for the hydrogen, 2 for the hydrogen, 2 for the hydrogen. Everything is good. The chlorine now has 8, and the carbon, you can see, now has 8 as well. So it looks like everybody's happy. Are all necessary octets complete? The answer is yes. All necessary octets are complete. Now we want to go into naming covalent compounds. How do we name and write formulas for basic molecular compounds? So writing, they're made of 2 nonmetals. The element in the lower group is usually written first except for hydrogen. Hydrogen is the only one that doesn't follow that rule. If elements are in the same group, the one with the higher period is written first. Okay? The first nonmetal gets the name of the element. The second nonmetal's ending changes to "ide." And finally, the difference is, instead of not using prefixes, we use prefixes to express how many, because we are not able to determine that because things can form double, triple bonds. And so we need to make sure that we know how many are there, and so that we can figure out which bonds are being formed. So this all applies except we don't use a prefix when the first element only has 1. There is no prefix used then. And this is going to be reiterated right there. So we use the number system. Mono means 1, di 2, tri 3, tetra 4, penta 5, hexa 6, hepta 7, octa 8, nona 9, deca 10. So here we go. Here we have some practice here. SO2. SO2, well, that's sulfur and oxygen. Remember, it's going to be sulfur oxide, but we can't just leave it like that. So it's going to be sulfur dioxide. N2O, well, there are 2 N's. Because there are 2 N's, I have to name that. Dinitrogen monoxide. Because the second one only has 1, I put the mono. The next one is nitrogen dioxide. Then we go to carbon and chlorine. So carbon chloride, but how many chlorine? Carbon tetrachloride, very good. Cl2O7, 2 chlorine, 7 oxygens, so 2 is di, 7 is hepta, so dichlorine heptaoxide? Yes. PCl, notice the P is in a group before the Cl, so the P is written first. Okay, so this would be 1 phosphorus, 3 chlorines, phosphorus trichloride, very good. 1 sulfur, 6 fluorines, sulfur hexafluoride. 3 silicons, 4 nitrogens, that's trisilicon tetranitride. Very good. All right, this is a little different because we have a bromate group. So this is nitrogen pentabromate. So we're using the same thing. Now, this would not be one that I would test you on. This would not be one that I would test you on, so don't panic about that. Okay, H2O. Dihydrogen monoxide, also known as water. So we can use the common name for that one, but it does have a chemical name as well. So let's look at a few more. So here's going backwards. Phosphorus trioxide. Well, that's 1 P and 3 O's. Very good. Dinitrogen pentacarbide. Nitrogen and carbon. Okay, so N2C5. Tellurium nona iodide. Known iodide. So TEI9 is correct. Carbon monoxide, that's CO. Selenium heptafluoride. Well, hepta means 7. There's only 1 selenium, so SEF7. Tetraphosphorus decoxide, P4O10. Arsenic hexabromide, ASBR6. And silicon dichloride, SiCl2. So hopefully you've gotten a little bit from this and you have a better understanding of what you need to do. So we are going to end right there.